Hi guys, take our journey of alcohol phenols ahead, and this is the lecture on chemical properties of phenols. And deliberately we have kept phenols and alcohols separate because of resonance of the phenols that creates a lot of disparity in the chemical properties of alcohols and phenols. So without wasting any time, सीधा screen के ऊपर dive करते हैं और चलते हैं chemical properties of
Let's get started with the chemical properties of phenols, and I am very sure that you must have gone through the video of chemical properties of alcohols. They are pretty relatable. So right in front we have the flow chart of the chemical properties of phenol. We'll just pick up each reaction one by one. Acidity of phenols. Phenols have O attached to H, which have electronegative difference. As a result, guys, these electrons will be more attractive towards this more electronegative species, and they are bound to break. Best part is, if they break, we get phenoxide ion. This is resonance stabilized. As a result, so if you want, I can just draw one resonating structure. This goes here. So this is phenoxide. Phenoxide showing resonance. For very simple reason that when ROH breaks, it gives us alkoxide and H plus. So this is very clearly explaining why phenols are better acid, because phenoxide is better resonance stabilized. You take phenol, treat it with any strong metal, hydrogen is bound to come out. Sodium phenoxide will be the salt form. Similarly, you treat it with NaOH, same reaction, only the byproducts will be different. You treat it with sodium carbonate, again we get water, carbonate is there, we get carbon dioxide, and we get phenoxide. So these are some acidic reactions. Please note, it does not react with bicarbonate because it is a weak base, and this is not a very strong acid as carboxylic acid, but carboxylic acid, they react with bicarbonate to give carbon dioxide. So this reaction can be used as a test to distinguish between phenols and carboxylic acid. Carboxylic acids will give bicarbonate test, but phenols will not give, being weaker acids. If you have electron withdrawing group, it will increase the acidity. If we have electron donating group, it will decrease the acidity of phenol. So that was all about acidity. Next, what we are going to do is, we are going to cleave this bond, right? So again, due to resonance, it is not possible. If we can take phenol and take zinc and perform distillation at very high temperature, we will have benzene plus ZNO. So this is a very important reaction to get rid of OH, which otherwise is very difficult. Let's do substitution, electrophilic. So let's do few reactions where we perform electrophilic substitution on benzene ring. OH is strongly OP directing, as O has lone pair of electron. So much so that sometimes we don't require usual catalyst which are needed to generate electrophile. So most of the places you will see that the catalyst like AlCl3 or in nitration like we used to use sulfuric acid, they are missing. So let's do few reactions. The first thing what we do is bromination. We do bromination, and very interestingly, it doesn't require anhydrous FeBr3 or any Lewis acid. We take non-polar medium like CS2, CCl4 and we get usual ortho and para substitution. So, this is OH and we get it ortho, and 1 we will get para, and para always will be the major product due to steric reasons. If we take polar medium, if our medium is polar, and what can be a good example of polarity than water? So, if we take bromination in aqueous, so sometimes it is written as Br2 aqueous, so you have to understand. So, what we get is, we get all 3 positions are substituted by Br, and this is 2, 4, 6. We get 2,4,6 tribromophenol and we get HBr. So, I have balanced the reaction also. So, these are 2 cases of bromination. For nitration, again we have 2 cases. This is phenol, strongly OP directing. If we take dilute HNO3, with dilute we get orthoisomer and para-isomer. And here orthoisomers undergoes intramolecular hydrogen bonding. Isomers undergoes intermolecular hydrogen bonding. Let's see, look at the diagram to see. So, this plus and the negative charge on oxygen, they forms intramolecular hydrogen bonding, whereas this plus will combine with this minus charge on oxygen. So, they form intermolecular hydrogen bonding. So, intra will have low boiling point, whereas inter will have high boiling point, and their separation will be very easy. For the second case of nitration, there is no space. So, let me go down. We take conc HNO3, we can take some drops of sulfuric acid also, and we get substitution at all 3 positions like bromination. This is known as 2,4,6 trinitrophenol, commonly known as picric acid. This is a good explosive. So, this is the second case of nitration. Let us do sulfonation. Very low temperatures, we get ortho derivative, whereas high temperature, something like 373 Kelvin, we get para derivative. This is kinetically controlled and this is thermodynamically controlled. So, we get both the products at different temperatures. Try and perform Friedel-Taft alkylation or acylation. The yield is very poor. Oxygen atom has lone pair of electron and this is Lewis acid. So, this coordinates with lone pair of electron and products are the products of very low yield are formed. So, you have para as major product and very small amount of ortho products are formed, very small amount. If you take phenol and you treat it with benzene, diazonium chloride in weakly alkaline medium, coupling reaction takes place. This is known as coupling reaction. Now, here what happens is, this part is an electrophilic center, this part acts as an electrophilic center. So, at ortho or para position this gets attacked, but we know that at ortho there will be steric hindrance because this electrophile is huge. It's a big electrophile. So what happens? We get para product. And what para product we get? It's a very interesting product. We get para hydroxy azobenzene. This is orange dye. So this can be taken as a test for phenol. This can be taken as test for phenol, test for diazonium. When we take phenol, we treat it with NaOH. A very obvious product is we get sodium phenoxide. So what I am trying to tell you is I am trying to write two named reactions simultaneously, help you out with that. You have water coming out here, and what you do is you treat it with carbon dioxide at about 400 Kelvin. Now guys, just see this carbon dioxide whose structure is like this, it again acts as an electrophilic center. This has got a plus and this has got a minus. So at the ortho position, the charge density is high, so it attacks. At the ortho position, the charge density is high, so the attachment is via C, and what we get is further once we take H plus, right, this is nothing but salicylic acid, that is orthohydroxy benzoic acid. The same reaction, exactly the same reaction with these steps remaining same, and if we treat here with chloroform, so what we get is ONA, and here what we get, we use chloroform and then simultaneously hydrolyze it with NaOH. So what we get here is, we get here CHO, which again if we use HCl or any dilute acid, we will get OHCHO. The same can be performed, the same reaction can be performed with carbon tetrachloride followed by hydrolysis NaOH, and what we get here is, which further undergoes acidic hydrolysis to give you the final product, that is salicylic acid or orthohydroxybenzoic acid, and this is aldehyde or salicylaldehyde. So guys, if you look at these reactions, this reaction is known as coal-base reaction, will have para products as well, but coal-base is for ortho product reaction, that is, this is the first step, this is the second step, and these are the rest of the steps. This is known as Reimer-Tiemann. So Reimer-Tiemann reaction we can use with chloroform, or also we can use carbon tetrachloride. Reduction. So as we all know, it is very difficult to reduce benzene ring. So phenol, when undergoes reduction in presence of nickel and a very high temperature of about 533 Kelvin, the benzene rings reduces. All the double bonds, they get reduced, and we have cyclohexanol, right? So we will have one H here, one H here, one H here, one H here, all double bonds gone, and this is known as nothing but cyclohexanol. In alcohols, it was very easy to oxidize an alcohol because this bond can easily give you C double bond O, OH, right? But in benzene, this single bond is very difficult to get oxidized to C double bond O, right? And so what happens is, when we use potassium dichromate or sodium dichromate, which are very strong oxidizing agent in H2SO4. What we get is the benzene ring oxidizes, and this is known as para-benzoquinone. It is a conjugated dione. So there are two ketonic groups. So if you want, you can work out on the, if you wish, you can work out on the IUPAC name of this. So this is nothing but cyclo. So this is one position, this is the second position, cyclo, hexa, 2 comma, let me put the positions, 2 comma 5 diene, 1 comma 4 dione. So that will be the IUPAC name. So this is the last reaction for phenol.
So that was all about chemical properties of phenols. और आपको लग रहा होता कि reactions कितनी repetitive हो रही. So we meet in the next class with another interesting topic. Till then, take care of yourselves. Bye bye.